The heart of statistical analysis is in this thing called the hypothesis test. The hypothesis test makes some claim about a population parameter. We've got an alternate hypothesis that we're going to try and prove. This video is going to kind of look at the setup and the theory behind a hypothesis test. And then future videos are going to take a look at how we actually conduct a hypothesis test by calculating the individual values. The first thing we need to do for any hypothesis test, though, is identify the hypothesis that we are going to test. There's actually going to be two hypotheses that we take a look at in each hypothesis test. The first one is called the null hypothesis. The null hypothesis will always claim that the parameter equals a claimed value. So a couple examples that you might see for a null hypothesis. Notation's really important here, so you want to make sure you take note. The null hypothesis is a capital H with a lowercase 0 or a subscript of 0 with a colon. Then you'll see the parameter, maybe mu for mean, and it always equals some number. So maybe we've claimed that the parameter equals 10. This would be a null hypothesis if we were working with a mean. Another example of a null hypothesis might be that some population proportion is equal to maybe 3% or 0.03. That would be a hypothesis for a proportion. Notice the null hypothesis notation, the parameter, and what we claim it equals. Another null hypothesis that we might see is we could claim rather than the parameter equals a number, we could claim that two parameters are equal to each other. Maybe the average from group 1 is equal to the average from group 2. This would be a null hypothesis that compares two means to each other because we've got two groups. But the important thing that we see is the null hypothesis, h sub 0, shows that the parameter is equal to a number. The null hypothesis is what we're going to assume is true. Maybe we'll make a note of that. Assumed true. We're going to believe the null hypothesis is true until we can prove this thing called the alternative hypothesis. Here at the alternative hypothesis, we're going to claim that the parameter is either different, smaller, or larger than the claim. If the null hypothesis is what we assume to be true, the alternative hypothesis is what we are trying to prove. So some examples of hypotheses. For the mean hypothesis in blue above, we said the mean was equal to 10. Maybe an alternate hypothesis, which uses h sub a for alternate, will claim that same parameter is maybe different than or not equal to 10. If I were to draw a picture of what this looks like, is we'd have our normal distribution with our mean of 10 right in the middle. And we're trying to prove either that the mean is in that small left tail or the larger right tail, smaller or bigger. We call this a two-tailed test because we're OK proving the alternative on either side, bigger or smaller. In green, let's look at an alternative hypothesis for the proportion that was equal to 3%. Let's say a proportion we want to prove is smaller than 3%. We would say less than 0.03. And if we were to draw a picture of what this looks like, the claim at 0.03 in the middle, we're trying to show that we actually fall in the less than smaller side of things. We call this a left tail test. Oops, and I wrote two test. That shouldn't say two test. That should say two-tail test in blue. Then in gray, we said that the mean 1 was equal to mean 2. That was a null hypothesis. Let's say we wanted to show that the average of group 1 was actually bigger than the average of group 2. When we say greater than with our alternative hypothesis H sub A, that means we're going to assume maybe that there's no difference between them, that they're equal, but we're trying to prove we're on the right side in a right tail test, that the first average is actually bigger. So we can mix and match these all we want, but the alternative is either going to say it's different than a two-tail test, smaller than a left tail test, or bigger than a right tail test, what was actually claimed in the null hypothesis. And this is what we're actually going to try and prove. Let's look at an example. Example. A real estate agent claims that the mean rent in the community is $1,500. You want to show it is actually greater than that value. Well, if we were to set up our hypothesis for this, we would say that the null hypothesis, since we're talking about the mean, the symbol for average is mu, the mean is equal to, with the null hypothesis, the claimed value of 1,500. The alternative hypothesis, what we're trying to prove, is that the mean is actually greater than that same $1,500. And so if we were to draw a picture, the mean of 1,500, the claim is in the middle. And because we wanted to show greater numbers are off to the right, we have a right tail test. And that would be how we would set up this hypothesis in order to actually test it. Now, we're trying to prove that alternate hypothesis. We're trying to prove that the average is actually greater. But how do we prove it? Well, the way we prove it is we're going to collect some data to help us make a decision. Making a decision. The way we make a decision is we look at this thing called alpha. That's a Greek letter A. Alpha is what we say. Alpha is the smallest probability where we still believe the null hypothesis is true. Remember, we assume the null hypothesis is true, and we try to prove the alternative. And the standard we use is alpha. Alpha is the smallest probability where we still believe the null hypothesis is true. And we're going to compare it to this thing called the p-value. And the p-value is the probability our sample or more extreme is obtained. In other words, how rare is the sample we got? Is it rare enough to make us doubt the assumption that that null hypothesis is true? If we have a small p-value, where it is smaller than alpha, that means there's not enough evidence to still believe the null hypothesis is true, and our decision will be to reject the null hypothesis in favor of the alternative hypothesis. If we have a larger p-value than alpha, it's bigger than that smallest threshold, then we say we will fail to reject the null hypothesis. We could not disprove the null hypothesis. So for example, let's say that real estate agent we were talking about collected a sample and calculated. Let's say the real estate agent finds a sample with a p-value of 0.0381. The real estate agent is going to compare that p-value to the alpha. Let's say if the alpha was 0.01, notice that 0.03 is bigger than that. And so because the 0.03, the p-value was too big, too much evidence in favor of the null hypothesis, the real estate agent would fail to reject that null hypothesis. If the alpha, though, was picked to be a different value, let's say the real estate agent picked alpha to be 0.05. Now notice the p-value is smaller. If you have a small p-value, then we're allowed to reject the null hypothesis. We're going to reject that rent is $1,500. We're going to conclude that there's evidence that it's bigger than the $1,500. That's how we're going to make our decision. If the p-value is smaller, we can reject. If the p-value is larger, we fail to reject. One way we understood confidence intervals was with an analogy. So let's see if we can understand hypothesis tests with an analogy as well. Let's take a look at how a trial works in the US. In the United States of America, if someone is on trial, that person is innocent until proven guilty. And to be proven guilty, the evidence must be beyond a reasonable doubt. So if this was a hypothesis test, what we'd essentially be saying, the null hypothesis is that the person is equal to innocent. We always assume the person is innocent from the beginning. And the alternative hypothesis is what we're trying to prove. We're trying to prove the person is not equal to innocent. And maybe a better way to say that would be that the person is guilty. This is what we're trying to prove in a court of law. Well, how much evidence do we need to prove they're guilty? That decision point is reasonable doubt. We're trying to prove beyond a reasonable doubt. So we're going to present a bunch of evidence, and that evidence is going to calculate this thing called the p-value. And the p-value is going to ask, is it beyond alpha or smaller than alpha? Is it beyond a reasonable doubt? If it is smaller than alpha, if yes, it's beyond a reasonable doubt, then we can reject the null hypothesis and conclude the person is guilty. That's what we're trying to do. If it's not beyond a reasonable doubt, we fail to reject the null hypothesis, which means we're going to conclude they are not guilty, which is an interesting result. We never actually in a court of law prove somebody is innocent, and it's the same thing in a hypothesis test, is we'll never, ever, never, ever, ever prove the null hypothesis is true. We cannot do that in statistics. What we do say is that we failed to reject it, but we never actually proved the null hypothesis. The only thing that we actually can try and prove is the alternative hypothesis.